So our next speaker is Houcine Ben Dali from the Université de Lorraine, who will speak us about the matching Jack conjecture.
Sorry? Okay, thank you. I would also like to thank the organizers for this invitation. So my talk today is about this long-standing conjecture of Goulden and Jackson called the matching Jack conjecture. So today I give half an answer to this question by proving the integrality property using some surprising connection with the Farahat-Higman algebra. As you can guess, there is a remaining part of this conjecture to prove some positivity property yet to be proved. So I would like to start by some motivations about behind this conjecture, more precisely with this result of representation theory, which puts together sure functions and connection structure coefficients in the permutation in the symmetric group. So what we have on the left side of this equation is the sum over all integer partitions theta, and then up to some normalization factors, we have a product of the same sure function as theta, but expressed in three different power sum bases, which we denote P, Q, and R. And then what we do is that we expand this function in the power sum bases associated to these three different alphabets, P, Q, and R, and the coefficients which appear depends on, so always there's some normalization here related to the number of permutations of cyclic type lambda, and the coefficients which appear are indexed by three partitions, lambda, mu, and nu, which have the same size. And what we obtain is that these coefficients actually they count the number of ways to decompose a fixed permutation sigma lambda of type lambda into two permutations sigma 1 and sigma 2, which has respectively cyclic type mu and mu. Okay, so this is just a generating function version of two classical results of the representation theory of the symmetric group. So the first result tells us that sure functions, when you expand them in the power sum basis, basically we have the characters of the symmetric group which appear. And the second result gives us that tells that the structure coefficients in the symmetric group can be expressed as a sum of three as a sum of the product of three characters. So one other reason people are interested in such generating series is that it's also related to counting maps. So these coefficients actually they count maps on orientable surfaces. Just some graph drawn on an orientable surface. For example, here we have an example on the torus. And this is actually a consequence of the fact that these maps can be encoded by pairs of permutations. So the first thing that Goulden and Jackson proved is that we can do the same thing for another family of symmetric functions, which are the zonal polynomials, which I'm not going to define at least in this slide. And so it's always the same thing. We take the product of three zonal polynomials in three different alphabets of power sum functions. The normalization is a little bit different. And then when we expand this in the power sum basis, the coefficients which appear here has always a nice combinatorial interpretation, but this time we have matchings instead of permutations. So basically matching, we can think of them as a generalization of permutations, and more precisely, we have a bijection between permutation and some particular type of matchings, which are called bipartite matchings. And the idea of the proof is quite similar, except that here, instead of having a representation theory of the symmetric group, we have a Gelfand pair of the symmetric group and the pair octahedral group. And as always, we have a nice connection with maps. So this is also, this generating series also count maps, but now on general surfaces. And what I mean by general surfaces, these are maps orientable or not orientable. So a natural question arises here is that, is there a way to unify these two equations which look very similar? And at least on the algebraic side, this left side, these red objects, we have a natural candidate, which are given by Jack polynomials. So Jack polynomials are symmetric functions, always indexed by integer partitions, but which also depend on this one deformation parameter B. So actually, this is the definition of Jack polynomials given by MacDonald. It tells us that they are basically characterized by two properties, some triangularity property in the monomial basis and some orthogonality property with respect to some B deformation of the classical whole scalar product on the symmetric group. So this abstract definition is not very important for this talk. What's really important is that if we take B equals 0, basically Jack polynomials are sure functions, and if we take B equals 1, we recover zonal polynomials. So the idea of Goulden and Jackson is that, okay, we replace in this generating series sure functions or zonal polynomials by Jack polynomials, and then we expand them in the power sum basis. So we have some coefficients here which appear always indexed by 3 partitions of the same size, but which also depend on this deformation parameter B. And the question, do these coefficients have some combinatorial interpretation? So at least we know that for B equals 0 and B equals 1, this is the case. So this summarizes a little bit the two first slides. So for B equals 0, this counts pairs of permutation or equivalently bipartite matchings. And for B equals 1, this counts matchings bipartite or not. So what Goulden and Jackson conjectured in this matching Jack conjecture is that these coefficients, actually these C coefficients, actually they are a polynomial in the parameter, in the deformation parameter B. And these polynomials have non-negative integer coefficients. Okay, and it's not very difficult to see that given the results for B equals 0 and B equals 1, this algebraic formulation has a combinatorial reformulation, which says that actually this coefficient C can be written as sums over matchings. So what does it say is that we can define there exists some statistics on matchings which have non-negative integer values. And actually these statistics are supposed to quantify somehow the non-bipartity of the matching. So in particular, we ask that the statistic is 0 if and only if the matching is bipartite. And then this statistic also satisfies that we can write the coefficient C as sum over matchings of some types, and in which we assign to each matching this B weight of the form B to the power of its statistic of the matching. Okay, and actually what makes this conjecture hard and interesting is that we have, sorry? Yeah. Excuse me, I don't hear you.
Could you clarify what a bipartite matching means? Because I think it would always be, what I understand of a matching, it would always be bipartite.
Okay, so I didn't precise the definition, but basically we consider matching so these are perfect matchings, and we consider matching on the sets of even size, and so there are these integers and integers with hats, and a bipartite matching will be a matching relating always an integer without hats with an integer with a hat. So that's sorry, a hat. Sorry, excuse me. At the type.
And I also don't understand what the type.
Okay, I didn't define it because it's a little bit technical. We should fix two matchings, and we can think of it just as a generalization of permutation. But I can give more details about this later. So as I said, okay, we have no B deformation of this representation theory that allow to prove the results for B equals 0 and B equals 1. So we have to come up with some new techniques to deal with this conjecture. So a priori, what do we know about these coefficients? So just from the definition of Jack polynomials and some basic properties about power sum functions, we know that these coefficients actually are rational functions in B. So we are very far from the conjecture of Goulden and Jackson. And almost 20 years after this conjecture has been formulated, Dołęga and Féray proved that these coefficients actually are polynomials in the parameter B. And they obtained some upper bound on the degree of these polynomials. So I write it here with the in terms of ranks of these of these partitions. And what I call a rank is just the size of partition minus its length. And so what we should do now is to study the coefficients of these polynomials in order to obtain the matching Jack conjecture. And the result I present today is an integrality result. So we prove that actually the coefficients of these polynomials are integers. And so there is what is remaining to prove is that these coefficients are positive also to have the proof, the full conjecture of Goulden and Jackson. And actually, since the approach here is independent from the approach of Dołęga and Féray, we obtain a new proof of the polynomiality of the coefficients. Okay, so the starting point of the proof is what I call the matching Jack conjecture for marginal sums. And what I call marginal sums are coefficients indexed by two partitions of the same size, lambda and nu, and some integer m less or equal than n, and which are obtained by taking all this sum over all partitions nu over which has length m of this coefficient c with three partitions lambda, mu, and nu. Okay, and if we do this, so this results from a previous work, we prove that actually these marginal coefficients have this nice combinatorial interpretation predicted by Goulden and Jackson. And in particular, we know that these marginal coefficients are polynomial in B with no negative integer values. So just a comment on this result. So this is based on the work of Chapuy and Dołęga on the b-conjecture, which is another conjecture of Goulden and Jackson very related to the matching Jack conjecture. And the idea of their proof, they came up with the new differential operators, and they use some techniques in the equations, Tut-like equations on maps. And what we do, what we know about these techniques is that we cannot control more than two partitions and one integer. So combinatorially, we cannot, at least with these techniques, we cannot do better. So the idea of the of what I present today is to use some algebraic framework of this Farahat-Higman algebra to transfer at least partially this result to the coefficient C with three partitions. And what I mean by partial is that we transfer the integrality, but we lose the positivity. So the scheme of proof is the following. So we have integrality for the marginal coefficients, and we want to obtain the integrality for coefficients with three partitions. So the first ingredient is this associativity property that I will define in the next slide, which gives us a system of linear equations which relates the coefficient C with three partitions and this coefficient C bar, the marginal coefficients. And the second ingredient is the Farahat-Higman algebra, which says to us that this system is actually invertible in Z. So we obtain integrality information for the coefficient C. So you can already see here why we lose the positivity, because we have some system to invert and we cannot obtain the positivity information. And just one comment on this. So on this approach, this is quite surprising, because what you are saying here is that we have this associativity property which allows to cover the coefficient C with three partitions from the marginal coefficients. And even the fact that this system is somehow invertible, even in Q, we don't understand it combinatorially. And this have some nice applications. For instance, we can obtain a direct new proof of the matching Jack conjecture for B equals 0, B equals 1, which actually does not use representation theory. Okay, so now I will start by explaining what this associativity property is. So this is actually a consequence of the orthogonality of Jack polynomials, and which is given by this abstract relation for fixed four partitions of the same size. So I will try to give some combinatorial interpretation of this associativity for at least the case B equals 0, because when we take B equals 0, we know that these coefficients have a combinatorial interpretation in terms of permutations. And what we can see is that both of the sides of this equation, they count the number of ways we can decompose a fixed permutation sigma lambda of cyclic type lambda into three permutations, sigma 1, sigma 2, sigma 3 of respective type nu and nu and rho. So we have two ways to decompose, to have such a decomposition. Either we start by choosing the permutation sigma 1 of type lambda. So this will fix the product sigma 2, sigma 3 of some type kappa, and then we decompose this product. Or we can do the opposite. So we start by fixing sigma 3, and then we do the opposite, and we obtain the right hand side. Okay. So the associativity property for B equals 0 is just the associativity in the permutation group, in the symmetric group. So now what we are interested in is to have some relation connecting the coefficient C with three partitions and the marginal coefficients. So what we do is that we keep three partitions lambda, mu, and nu, and then we take the sum over all partitions row of length m, and we obtain this relation. Okay, so this is the marginal version of this associativity property. So how do we proceed? Is we try to prove that these coefficients C, lambda, mu, kappa are actually polynomials with integer coefficients by proceeding by induction over the rank of kappa. So how do we think of these equations? That we fix lambda and mu, and then we think of nu and m as a couple of parameters indexing this family of equations. So the idea is to select, let's say, a good set of parameters nu m, which allows to select the partitions kappa of rank less or equal and r, and to have some information about the partitions kappa of rank r. So, and to do this, actually, we use this upper bound on the coefficient C that I presented earlier. So we have this, let's say, the set of well-chosen parameters nu m that I denote with T, and those the definition is not very important. But what we know is that for this couple of parameters, we know that when we take the sum over all partitions kappa of rank R, and then we take the product of this coefficient C with three parameters and the marginal coefficients, this sum is a polynomial in B with integer coefficients. And which is what is important here is that the coefficients, the marginal coefficients which appear here, are actually a very particular type of marginal coefficients, which are called top connection coefficients, and are actually independent from the parameter B. And how do we think of this? So we think of it as a linear system in which the coefficients C with three partitions are the unknowns, and the coefficients encoding the system are the marginal coefficients. Okay, so what we want is to prove that the system is actually invertible in Z. So what we say is that, okay, we have the marginal coefficients here are independent from B. So the easiest thing to do is to think of them as their evaluation at B equals 0, because we know that for B equals 0 we have some nice combinatorial interpretation in the symmetric group. So that's what we do, and there is an elegant way to study the coefficient, the structural coefficient symmetric group, which is given by the Farahat-Higman algebra. So unfortunately, I don't really have the time to give the technical definition of this algebra. So I'll try to explain the main details of the proof in the context of the symmetric group. So I start by some classical definition. So if you fix a partition n of size, partition nu of size n, so denoted by C nu, the sum of all the permutations of type nu in the center of the algebra of the symmetric group. So this family of elements actually form a basis of this algebra. And what I recall from the first slide of this talk is that the structural coefficients of these elements are actually the coefficient C evaluated at B equals 0. And we know from this upper bound on the degree of this coefficient that we can restrict this sum over partitions kappa, whose rank are less or is bounded by the sum of the ranks of nu and rho. But here we are just interested in the case where we have equality here. So what we do is that we pass to the graded algebra, which is spanned by the same elements, C nu, but in which the multiplication is a little bit different. So it's just that we take the same sum, but we replace the inequality here by inequality. Okay. And so this is a graded algebra because all elements are have degree given by the rank of the partition indexing the element C nu. Okay, so and we note this homogeneous component of degree R by Z n R, and it's spanned by this C nu of rank R. So to sum up a little bit about the connection of these marginal coefficients with this algebra, so this can be seen as the coefficients of this family of elements, which is obtained as a product of some C nu with the marginal sum in the classical basis of the algebra of the symmetric group. And actually, what we prove is that this family is this spanning family for the algebra. And if we do this, we obtain that the coefficients here we are interested in, and which encode our system, are invertible in Z. So this is the idea of the proof. And what we really prove is that we can extract from this family of, we can choose a subset of T, such that actually this is a basis, up to some details of, okay. Just comment on this, so on this family of, on this new basis of the algebra. So these have two parts. The first part is the classical basis, and the second part is part given by the marginal sums. And actually, it's this is a result of Farahat-Higman that these sums they form an algebraic basis of the algebra. So we are kind of have we have an intermediate basis from the classical basis and the basis of Farahat-Higman and Higman. And just to comment on the proof. So first we have the stability property of Farahat and Higman, which have proven that proved that these coefficients C indexed by partitions of size n, they can be seen as structural coefficients also in the symmetric group of larger size, just by adding parts equal to 1 to the partitions indexing this coefficient. And actually, this allows to pass to the projective limit over n here. And this is actually the graded Farahat-Higman algebra. And it turns out that it's convenient to work in this algebra rather than the algebra of the symmetric group itself. And the second important ingredient of the proof is that we use two other bases of the algebra. The first one is the one I explained, given by Farahat and Higman, and the second basis given by Matsumoto and Novak, and which is basically the evaluation of the monomial function into the Euclid-Murphy's elements. And this diagram just illustrates the transition between the different bases which appear in the proof. Thank you for your attention.
Thank you, Houcine. Other questions?
Sorry, a very elementary question. I thought when b equals 0, there's a symmetry between lambda, mu, and nu, right?
Almost. Actually, there is a symmetry between mu and nu, but not lambda.
Not lambda, but
because actually we okay, I'll go back.
No, I know they're not living.
Okay,
But
here.
from
So
the
because
identity, I thought
because we fixed the permutation sigma lambda actually here. So there is
but if I look at the
because there is a z lambda here, which breaks the symmetry. But
Okay.
it's just a trick of normalization.
Thank
you.
Some more questions?
So do you get a combinatorial interpretation for the coefficients of the C lambda nu mu of B's?
Excuse me.
So you proved the integrality and polynomiality, right? So you prove, so if you have a non-negative integer coefficient, did you come up with some interpretation for them too?
So
It just comes from the linear algebra.
So yes, so the disadvantage of such an approach is that we don't really have a combinatorial interpretation, but I think that this kind of approach, it gives some idea for the to have the combinatorial interpretation for the coefficients, actually, because if you imagine that we have a candidate statistic on matchings, and we think of it, we think it's a good candidate for the matching Jack conjecture, what we might prove is that it's an answer for the marginal coefficients. And if we succeed to prove that it also satisfies this associativity property, this marginal associativity property, so it's also an answer for the matching Jack conjecture. But the problem is this associativity on the statistic on matchings, it's very hard because the matching that we use are built on maps, and the associativity is not very natural on them. So
So in fact, you don't believe that this method is likely to help in the other part of the conjecture, yes?
Sorry?
Understood, because there are two parts of the matching-Jack conjecture. The first one is polynomiality that you proved, and this is very strong result that was expected for a long time. And there is also other part that is coefficients in terms of interpretation of the graphs. So you think that your method, it will be complicated to use for that part, or to prove the whole matching-Jack conjecture.
Excuse me, can you repeat the, excuse me.
Sorry. Because for the whole matching-Jack conjecture, you have your part that is you prove that the coefficients are in fact polynomials with integer coefficients. And the second part is interpretations of the coefficients in terms of graphs. Yes. So did you make any progress with your approach on the second part?
So for the second part, you have this progression about the marginal coefficients.
Okay.
So yeah, this is so for now, this is I think the best we can do. And this is actually a consequence of the work of Chapuy and Dołęga about the b-conjecture. And I think that in this direction of combinatorial interpretation, for now, this is the best we can do. Yeah, this is a new statistic. Yeah. Exactly. And yeah, this is hard. I think. Yeah.
Okay. So thank you very much again.
Thank you.